When this image was transmitted from the International Space Station, the internet reacted exactly how you'd expect. They thought NASA had accidentally photographed an alien egg. Astronaut Don Pettit quickly clarified the situation. The bizarre specimen was actually Sputnik 1, a simple purple potato sprouting inside an improvised terrarium. The chaotic tentacles are the result of the microgravity morphological shift. Without gravity telling the plant which way is down, the physical structures reach out erratically in every possible direction. For the past 25 years, astronauts have maintained small, manual gardens like this. Tending to plants provides a sensory bridge to Earth, helping crews manage the severe isolation of low Earth orbit. Public attention focused on the strange visual, but space agencies saw a necessary biological prototype, required to solve a mathematical certainty regarding deep space travel. A crewed mission to Mars involves a rigid, non-negotiable timeline. The journey requires a minimum of 3 years for a round trip. This chart plots the nutritional potency of current pre-packaged space food over a 36-month period. The food remains relatively stable initially, but the vitamin viability drops sharply past the 18-month mark. That steep decline creates a severe malnutrition gap. During the entire second half of the voyage, the crew would face progressive dietary failure well before they even reached the Martian surface. To survive the journey, the crew must completely sever their reliance on Earth's supply chains. They have to operate an autonomous life support engine and grow their own calories in transit. Choosing what to grow is governed by the nutrient density doctrine. Inside a spacecraft, every single cubic centimeter of volume and watt of power is strictly rationed, meaning a plant must justify its existence through pure caloric output. This stacked bar chart compares the edible biomass of a potato against traditional staples like wheat and corn. While grains require intense processing and yield massive amounts of inedible stalks, nearly the entire potato plant contributes directly to the crew's survival. The vivid color of the Sputnik 1 potato serves a highly specific biological function. The dark purple flesh is packed with chemical compounds called anthocyanins. Anthocyanins are heavy antioxidants. In deep space, consuming them helps shield astronaut DNA from severe oxidative stress caused by cosmic radiation. Space agencies do not select crops based on dietary preference. The plants are carefully engineered to mitigate the lethal physical threats of living in a vacuum. Growing those crops requires specialized hardware. Early experiments used the manual Veggie system, but as you can see from the cramped, equipment-heavy interior of the station, manual farming takes up hours of necessary crew time. A Mars-bound crew cannot afford to spend their days gardening. NASA's solution is the Advanced Plant Habitat, a hardware platform focused entirely on systemic autonomy. It manages hydration, regulates the lighting, and nutrient delivery with zero human intervention. The push to close the caloric loop has triggered an international agricultural space race. While the US optimizes automated water-based hydroponics, the European Space Agency is engineering bioregenerative systems that use microorganisms to recycle organic waste directly into fertilizer. To prove these systems work, international agencies isolate them in Earth's most unforgiving environments. The German Aerospace Center pressure tests their automated hardware inside the Eden ISS greenhouse, operating entirely within the desolate, frozen landscape of Antarctica. Reaching Mars requires merging these distinct strategies. By synthesizing American automated hardware with European closed-loop recycling, engineers can construct a permanent, self-sustaining off-world ecosystem. The ISS has hosted continuous human occupation for a quarter-century. This extensive timeline transforms decades of localized orbital gardening into a massive, unified dataset on plant physiology in microgravity. The biological data extracted from experiments like the Sputnik 1 potato is actively dictating the physical architecture of upcoming permanent moon bases, establishing exactly how autonomous agriculture fits into the Artemis hardware. These immediate lunar deployments represent a clear transition point. Humanity is testing the exact technologies required to operate as an interplanetary civilization, completely independent of Earth's resources. The strict limitations of farming in orbit are simultaneously accelerating how we produce food on Earth. Commercial vertical farms in dense urban centers like New York and Tokyo now license the highly specific red, blue, and green LED light recipes originally engineered to maximize zero-gravity crop yields. Because lifting heavy water into space is prohibitively expensive, space-grade hydroponics were engineered to use 90% less water than traditional soil farming. Those exact systems are currently producing high-yield crops in drought-stricken regions worldwide. The need for absolute sterility on the ISS drove major breakthroughs in air filtration and ethylene gas scrubbing. Deploying these scrubbers terrestrially actively controls pathogens and drastically extends the shelf life of produce in grocery stores. The twisted purple potato photographed in orbit serves a dual purpose. It is the biological engine designed to sustain human life on Mars, while actively reinforcing the agricultural systems we rely on at home.